Hey class. The first type of bonding that I want to talk about is that of the ionic bond. And as we talked about in the last video, ionic bonds exist between metals and nonmetals. Um, and in this ionic bond, which we said was characterized by a transfer of an electrons, we see that it being an ionic bond, that it is unsurprisingly composed of cations, one type of ion, and anions, another, where cations have that positive charge and anions have that negative charge. And what we're going to see is that the metallic cation is going to transfer an electron. So we're going to have electron transfer from the metal to the nonmetal. And to kind of conceptualize this, which we show to the right with that little figure, we can think about what ion formation looks like. So let's look at the formation of a cation using something like sodium. So we start out with sodium metal, and to form that cation, that means we're going to lose an electron, and in that loss of an electron, we form a positively charged species, in this case, Na+. And then when we talked about anion formation, we said that we can take some atom, let's in this case say that's chlorine, we add an electron to it to get an imbalance of protons relative to electrons, and we get Cl minus. And we can see what actually happens here when we think about cation formation and anion formation is that they're linked, and we can take this electron we produced and consume it right here. And if we take, the two species we have, sodium plus and chlorine minus, this metal cation and this nonmetal anion, we can get something like Na plus Cl minus, which you might recognize more often as NaCl or table salt. But anytime you see NaCl, we want to remember that that actually is a sodium cation plus a chlorine anion. And so the way that this looks like, we can think about having our metallic sodium, looking at our figure to the right, and our chlorine gas. And your sodium is all of these little brown balls, and they're present and they're neutral. And you have your chlorine gas, which are these green ones right here. And so this is an example sodium. Right here is an example sodium atom. So it has 11 protons and 11 electrons and 12 neutrons. And so since it has 11 protons and 11 electrons, it's at charge neutrality. But it can give up an electron to become the sodium cation with 10 electrons and 11 protons. You have that imbalance where you have more protons than electrons. And that electron can be given to chlorine, which goes from 17 electrons and 17 protons to 17 protons and 18 electrons. You gain one electron here. You have an imbalance, so you get a -1 charge. And then these two ions, the sodium cation and the chlorine anion, they can come together through something called electrostatic forces. And the easiest way to think about this is you can think about these forces are like a magnet. Forces are like a magnet, where when you take two oppositely charged ions, in this case sodium and chlorine, it's like when you take two oppositely charged parts of a magnet, the two poles. And when you do this, you have opposite charges attract. And the strength of this attraction is determined by something called Coulomb's law. And so the expression we use to think about ionic attraction when you have oppositely charged ions, so this is for opposite charged ions, or repulsion, and this is for the same type of charge, or similarly charged ions, so same charged ion, is given by the expression below, this Coulomb's law, where the energy of that attraction or repulsion is proportional. That's what this little guy right here is. This just means proportional, which all that means, proportional. All that means is that I've dropped out a couple of the terms in this formula just to narrow it down to what's important. And so That proportionality says that if you take the charge of one of your ions, so this is ion 1, you take the charge of your second ion, we'll say that's ion 2, and you divide it by the distance that separates them, you get the energy of attraction and repulsion. And you'll often see this written as Q1, meaning charge 1, times Q2, which is charge 2, divided by R, which is the distance. And when you have two oppositely charged ions, so a positive and a negative, you get a negative value for the energy, so negative energy, and that means you have an attractive force. So a negative value means attraction. And then if you have a positive energy coming from either a positive charge times a positive charge or a negative charge times a negative charge, that gives you repulsion. And we can look at the two features of this Coulomb's law and think about how changing each of those features might affect the energy. So if we have a higher charge or a larger charge, since that's in the numerator, as we increase charge, that also increases the force. So this is a higher charge means more force slash energy. And then if we look at the distance that separates your ions, and an increase in distance comes from changing the size of your ions. As ions get bigger and they have a larger separation, the value in the denominator grows larger. This distance term right here gets larger, and so you have less force or energy as that distance increases. And when you have these two charged particles that are attracted to each other through Coulomb's law, they form something called a lattice. And what a lattice is it's a 3D structure composed, so 3D structure composed of many ions in an alternating pattern. So when you take a little crystal of sodium chloride, what that actually looks like is you have sodium, so a sodium cation, right next to a chlorine anion, but then they organize themselves by basically alternating in a giant 3D cube. So your brown spheres here are the purple ones here. So brown is equal to purple, and then green is equal to green, where you have alternation in all directions. So if you have a sodium right here, there's a chlorine behind it, there's a chlorine to the left of it, there's a chlorine above it, and there's a chlorine below it. And so in any direction you go, X, Y, or Z, left to right, up to down, or back to front, you alternate in the identity of the ion. Sodium, chlorine, sodium, chlorine, sodium, chlorine. And then at the macroscopic view, we just get one of those little crystals of sodium chloride. But if this lattice is this huge structure with many ions in an alternating pattern, we might have something like a single crystal of sodium chloride might be something like 500 sodiums and 500 chlorines. And so we need a way to better represent this so we know, what is the simplest way to depict this. And that simple way that we talk about the atoms or elements that make up a ionic bond or an ionic compound is the formula unit, where this is the basic form of an ionic compound. And when I say basic, what I really mean here is it's the smallest or most reduced. So smallest, most reduced electrically neutral. This is very important. So this neutrality is going to be very key here. Electrically neutral. Let me just respell neutral here so you can read that. So electively neutral collection of ions. And so instead of saying, sodium 500, chlorine 500, because there's, the same number of each of these, we can reduce that down into NaCl. And we can see that, we talked about NaCl is actually Na plus Cl minus, and we see that we've reduced it down to the smallest number, 1 and 1, and this formula unit we have has charge neutrality, or electrical neutrality, because we have a single plus charge and a single minus charge that will cancel each other out, okay? However, sometimes things are not that simple. So I moved this on accident. Okay, there we go. Sometimes things are a little bit more complex, and we don't always have a 1-to-1 ratio. Sometimes we have ratios that are a little bit different, so it's really nice and easy when we have something like sodium chloride. But sometimes we have something that has a form that looks like this, K2O. Or sometimes we have something like this, AlCl3, where these small numbers that we have right here, this 2 and this 3, which we call the subscript that's applied to each one of the elements, that subscript, that number, describes how many of that atom, or how many of that element. How many of that element. So sometimes we don't have this 1-to-1 ratio. And if we don't have a 1-to-1 ratio, that must mean that the charges on these species are different. So whereas sodium and chloride had a +1 and a -1, it must mean that potassium and oxygen, if they give charge neutrality, there must be a difference in charge. The same with aluminum and chlorine. And so the way that we can determine what that charge is we can look at the proximity of each of our elements to the noble gases. And so in that last video, we talked about the noble gases are known to have increased stability. And that's due to the number of electrons they have, as well as how those electrons are configured or located. There's this high stability with the configurations of these noble gases. And so we can look at taking our periodic table and basically folding it in on itself. So forming a little cylinder where we can put the first column of the periodic table right next to the 18th column. So the column that has hydrogen, lithium, sodium, potassium, we can put that right next to helium, neon, argon, krypton, etc. So this right here is going all the way over to here, okay? And so what we'll observe is that our metals, in order to get, when they're really close to the noble gas, to basically get to that noble gas configuration, what they're going to do is they're going to lose electrons to get to noble gas state. And so if we look at those metals, they're in column 1A, so things like lithium, sodium, what they're going to do is they're going to lose 1 electron. Lose 1 electron. Those metals that are in column 2A, so things like magnesium and calcium, what they're going to do is they're going to lose 2 electrons. And then things like aluminum, which is in column 3A, or that's also known as column 13. So column 13, aluminum is going to lose 3 electrons. And so where the metals are going to lose electrons, we expect the nonmetals to gain electrons. And they're going to gain the electron to get to a noble gas state. So fluorine is going to pick up an electron to become neon, or to look like neon. Chlorine is going to pick up an electron to look like argon. Bromine is going to pick up an electron to look like krypton. Okay? And so things like fluorine, which is in column 7A, which is also known as column 17, so fluorine, that's going to gain 1 electron. Things that are in column 6A, also known as column 16, like oxygen, that's going to gain 2 electrons to look like a noble gas. So it has to gain 1 to look like fluorine and then gain another to look like neon. And then things like nitrogen, which is in column 5A, also known as column 15, that's going to gain 3 electrons to look like neon. So neon gains 1 to look like oxygen, another to look like fluorine, and then a third to look like neon. And so really, what this all boils down to is you just have to look at if it's easier for a metal to lose electrons to look like a noble gas or to gain them. And so if we look at a couple of examples, we're going to be able to see what that looks like. So if we think about lithium, which starts out with 3 protons, it can either look like helium, which has 2 protons and 2 electrons, so 3 protons, 3 electrons, or it can look like neon, which has 10 protons and 10 electrons. And so we say to ourselves, is it easier for lithium? The difference between lithium and helium is 1 electron. So this is a loss of 1 electron. Is it easier for lithium to lose 1 electron or to look like neon, which would take, going from 3 to 10, gain 7 electrons? And so it should seem pretty obvious to us that, 1 is less than 7, so lithium is going to lose an electron to go from 3 electrons to 2, rather than gain 7 to go from 3 to 10. And you can do the same thing for something like nitrogen. Nitrogen starts with, excuse me, 7 electrons. And so nitrogen can either start to look like helium, which has 2 electrons, or it can try to look like neon, which has 10 electrons. So we can see that to go from nitrogen to helium, it would have to lose 5 electrons, but to go from nitrogen to neon's configuration, it only has to gain 3 electrons. And so you just go whichever direction is closer. So it's a lot easier to go from 7 to 10 than it is 7 to 2. So nitrogen picks up those 3 electrons to become N3 minus. Okay? Alrighty. And so what I'll have you all do is to just utilizing that same basic framework, I want you to think about what charge each of these is likely to adopt. So I'll have you pause the video right now and determine what charge you'd expect each of these atoms to adopt. Okay? All right, welcome back. And so if we look at each of these, we can look at their proximity to the nearest noble gases. And so aluminum is close to neon, which has a Z equal to 10. And remembering that Z is our atomic number, which is equivalent to our number of protons. So aluminum has neon is the noble gas that came before, and then the noble gas that comes after is argon, and that has a Z equal to 18. And so we ask ourselves here, is it easier for aluminum to lose 3 electrons, to go from here to here is lose 3 electrons, or is it easier for aluminum to go and, in this case, gain 5 electrons? And we see that, the loss is smaller than the gain. So we'd expect aluminum to lose 3 electrons and become Al3+. Now we can look at strontium. So strontium has an atomic number of 38. The nearest noble gases are, the one before is krypton with a Z equal to 36. And then the one that comes after is xenon with a Z equal to 54. And so there's a little bit more nuance here that we'll get into later on, where the electrons that are put into locations where there's transition metals are a little bit different here. But we could see that the difference between strontium and krypton is 2 electrons, whereas the difference between strontium and xenon is 16 electrons. So that's, much, much larger. And so in this case, it shouldn't surprise us that strontium adopts a 2+ charge, which we can see right here. Strontium 2+ here, aluminum 3+ here. The last one we have is sulfur. And so the noble gas that's before sulfur is neon with a Z equal to 10. And the noble gas that comes after sulfur is argon with a Z equal to 18. So we're always going to look at the noble gas that comes before it and the noble gas that comes after it. And so we can see that to go from sulfur to neon, we'd have to lose 6 electrons. And to go from sulfur to argon, we'd have to gain 2 electrons. And we see that, 2 is smaller than 6. So we expect sulfur to gain these electrons and to become sulfur 2-, which we can see right here. Okay? All right. And so now that we've thought about each of these different charged species, we can think about, taking the charged species and forming ionic compounds. And we'll remind ourselves of a couple traits we observed when we looked at sodium chloride. We want to make sure that in each of our ionic formulas, which can have, a single one of our cation or an anion or multiples of either, that we contain positive and negatively charged ions. So positive and negative charged ions. So that was our first thing, typically coming from a metal and a nonmetal. The second thing we want to make sure when we have these ionic formulas and the formula units is we want the sum of charges should equal 0. Or another way to say that is that they should cancel out. So cancel out. And what that means is that your, your charge from cations must equal your charge from anions. And I'm putting cations and anions to say if you have multiple of the cation or multiple of your anion. And we want to make sure whenever we write these formula units, we want the formula reflects the smallest whole number ratio of ions. Okay? And so what we're going to see is that many elements are going to form ions of a predictable charge. So formula reflects. Okay. Just give it a second here. Smallest whole number ratio of ions. Smallest whole number ratio of ions. Okay, and so those elements that typically adopt predictable charges are shown to the right. So sodium, lithium, potassium, magnesium, fluorine, chlorine, etc., etc. And so we're going to utilize the fact that these things form predictable charges to help us in forming the formula unit. And so if we're confronted with something that, has elements that in most cases have an unequal charge relative to each other, we can determine what the formula unit is by following a simple algorithm or pattern here. So the first thing we want to do is write out the symbol for charge versions of the metal and the nonmetal. And you can do this regardless of if you have a predictable charge or a unpredictable charge. But in this case, we're going to start with those that have predictable charge. So if we look up at our table above, we see that aluminum is a 3 plus right here, and oxygen is a 2 minus right here. So we have Al3 plus and O2 minus. And then now that we know the charge version of each of our species here, we want to determine what the ratio of each of those is that leads to a charge neutral state. And the easiest way to do this is by doing something that I'll refer to as cross multiplying. And what that means, so cross multiplying, what that means is to determine in the formula Al, some certain number of Als given by X, with some certain number of oxygens given by Y. If we're trying to figure out what each of those numbers are, the X and the Y that are supposed to be our subscripts, we can cross multiply. And that means that you're going to take the charge of one species and put as the subscript of the other. And this makes a lot more sense. Script, I put SR instead of SC. This makes a lot more sense when you do it in practice. Of other. And so if we have something like Al3 plus and O2 minus, we can write them right next to each other. And then what we can do is we can take the charge on one and bring it down to the subscript of the other. So we'll take the 2 from oxygen and put it down by aluminum. So Al2, then we have oxygen. We take the 3 from aluminum, write that as the subscript for oxygen. So we have Al2O3. So we say that x is equal to 2 and y is equal to 3. And what each of these numbers are is this 2 is simply the charge of oxygen. And this 3 is the charge of aluminum. And once we've done that, this cross multiplication, we wrote each of them next to each other and then took the charges and then multiplied them across to put it in the subscripts. Once we've done that, if necessary, so this would be if necessary, divide by common factor. And we would see this if we had something like barium and oxygen. We look up in our table and we see that barium has a 2 plus and oxygen has a 2 minus. And if we cross multiplied those, we'd get Ba, 2 from the 2 minus on oxygen, oxygen 2 from the 2 plus on barium. And we see that each of these has a 2 as a subscript. So if we divide both of those subscripts by 2, we'd get BaO, which is our simplest, most reduced form for barium oxide. And then finally, continuing with our aluminum oxide example, we want to make sure that our charges cancel out, that we have charge neutrality. So we know that we have 2 Al ions, and each of those Al ions has a plus 3 charge. And so we'll take 2, the number of our ions, times the charge, plus 3. We get that's plus 6. And now we're going to look at our oxygens. We have 3 oxygen ions, and each of those oxygen ions has a minus 2 charge. So we take our number of oxygen ions, multiply it by the charge, we get that we have negative 6. So we have a plus 6 and a minus 6. They're equal and opposite, and so they cancel out, and so this checks out. Okay? All right. And so in the next video, what we're going to do is we're then going to talk about how we can name these compounds now that we know how to construct their formula.